Welcome to Space Science. Tonight, the journey begins at the farthest edge of the visible universe and moves slowly back toward Earth. Out there, distance is not the only danger. Time changes, space expands, and at some point, going farther may no longer mean exploring. It may mean never coming home again. From the cosmic horizon to the final fire of re-entry, this is the story of how far into space humanity could go before return becomes impossible. If this kind of deep space journey fascinates the mind and helps the night grow quieter, please like the video, subscribe to Space Science, and settle in for the full voyage. At the widest scale known to astronomy, space appears as a visible sphere centered on Earth, only because light needs time to travel. This is not a true center. It is only the limit of what can be seen from one particular place during one particular age of the universe. Beyond that limit, there may be more galaxies, more darkness between them, and more of the same broad structure continuing outward. Yet none of that farther realm can be observed directly, because its light has not had enough time to arrive. The largest possible outward journey therefore begins with the simple fact: even before any engine starts, much of reality already lies beyond contact. The observable universe is often described as the region from which light has reached Earth since cosmic expansion begins. That expansion starts in the hot early state usually called the Big Bang. This phrase does not describe an explosion into empty space. It describes space itself changing, stretching, and cooling. Matter gathers. Light decouples from matter after the first long interval of extreme heat. Stars and galaxies form much later. Over billions of years, the distances between large cosmic structures grow. When astronomers measure the deep sky, they find that remote galaxies are not mainly moving through space, away from one another like fragments from a blast. Instead, the fabric between them expands. This distinction matters because a return journey depends not only on speed, but also on whether the road itself changes while a traveller is on it. On human scales, distance is often imagined as something fixed. A road between two cities remains roughly the same length from one year to the next. In the wider cosmos, this assumption breaks down. Space grows. The farther one looks, the more strongly this growth shapes the scene. Galaxies at immense distances recede because the space between them and the Milky Way expands. For the most remote visible regions, this recession is so strong that no ordinary idea of pursuit feels intuitive anymore. A spacecraft may move in one direction, but the great background geometry still evolves beneath that movement. Because of this, the question of going so far that return becomes impossible begins not with fuel or biology, but with the horizon built by light and time. There is a cosmic horizon because the universe has a finite age. If the cosmos were infinitely old and unchanged, light from arbitrarily distant places would already have arrived. Instead, there is a limit to visible distance. That limit is not equal to the age of the universe multiplied by the speed of light in a simple way, because the space through which the light travels has expanded during the journey. The result is a much larger present-day distance to the farthest visible matter than a first estimate would suggest. Astronomy therefore presents a calm but severe picture. The most distant regions now seen are already astonishingly far away, and they are seen as they once were, not as they are now. This introduces another deep barrier to return. Any journey to very great distance is also a journey into old light. A galaxy observed in the remote universe appears as it existed billions of years in the past. If a traveller could somehow depart toward it, the destination would not remain the same place in a static stage set. Time would pass, Stars would age, orbits would change, mergers might occur. The traveller would chase not the ancient image in the telescope, but a moving reality carried onward by cosmic history. Return would be shaped by this same delay. Earth too would continue through time. Even if a path outward were somehow direct, the meaning of home would slowly shift while the traveller crossed the abyss. At the larger scale, the universe also appears nearly uniform in every direction when averaged over enough distance. Galaxies cluster locally, but the broad pattern becomes statistically even. This means there is no obvious outer wall, no physical shell where matter stops and a traveller strikes a boundary. Instead, limits come from causality. Causality is the rule that influence cannot travel faster than light through space. If two regions become too widely separated by expansion, signals from one may never reach the other. A return then ceases to be difficult and becomes physically excluded by the geometry of the cosmos. The issue is not courage or endurance. It is whether any message, any probe, or any ship can still remain inside a shared region of possible contact. Modern cosmology indicates that the expansion of the universe is not merely continuing but accelerating. Observations of distant exploding stars, together with other measurements, support this view. The cause is usually described through dark energy, a name for the process or property linked to this acceleration. Its exact nature remains uncertain. Observations indicate that acceleration is real. It remains uncertain what dark energy fundamentally is. For the problem of never returning, the effect matters more than the label. Over immense spans of time, more and more distant galaxies move beyond the reach of future interaction. Light emitted from them now may still be seen if it began its journey long ago. Yet a signal sent from Earth today may never arrive there. This creates a difference between what can be seen and what can still be visited in principle. The visible cosmos is larger than the region with which future two-way contact remains possible. There are galaxies whose ancient light reaches Earth, while Earth's present cannot reach them back. In that sense, some parts of the sky are already one way in principle. They are not travel destinations for a civilization that hopes to return information home after an unlimited wait. The ancient photons arrive as witnesses from a region that is, in practical causal terms, slipping away. At this outermost scale, there's also no meaningful shelter, no solid frame, and no nearby source of energy that can be imagined as support for travel. Intergalactic and intercluster space contains thin gas, radiation, magnetic fields, and scattered particles. But it is mostly emptiness beyond ordinary intuition. A journey beginning here is not merely long. It is set inside an environment so dilute that familiar comparisons fail. There are no landmarks in the human sense, only patterns of light and gravity spread over incomprehensible distances. The silence of this scale is not emotional, it is physical. Matter is sparse, encounters are rare. The journey is dominated by geometry rather than terrain. So the first answer emerges at the widest boundary, before considering galaxies, stars, or the solar system. The universe already contains regions from which return is impossible in principle, because expansion, finite cosmic age, and the speed limit of light divide reality into zones of possible and impossible contact. The observable horizon is not a reachable rim, but a statement about what light has had time to do. Beyond it, there may be more cosmos. Within it, some distant realms are already receding into permanent separation. The farthest outward journey therefore begins with a quiet conclusion. Space is not only vast. At its largest scale, it is arranged so that some departures would leave Earth not merely far behind, but forever outside the circle of return. Beyond the widest visible horizon, the universe cannot be mapped directly, but within the horizon its matter does not lie in a smooth mist. On the largest scales that can be measured, galaxies gather into a vast pattern, often called the cosmic web. This web is not woven from threads in any literal sense. It is a structure of enormous filaments, crowded knots, and wide voids. A filament is a long region where many galaxies and great clouds of gas collect under gravity. A void is a region with far fewer galaxies than average, seen across hundreds of millions of light years. The cosmos resembles foam or branching roots more than a random scatter of lights. This is the broad landscape through which any extremely distant outward path must pass. The web forms because matter in the early universe is not perfectly even. Tiny differences in density appear in the hot young cosmos. Over immense time, gravity slowly enlarges those differences. Slightly denser regions pull in more matter. The inflow strengthens the density further. Gas and dark matter accumulate along preferred paths, and the result is a network of structure stretching across unimaginable distances. Dark matter is the invisible form of matter inferred from gravity. It does not shine, and it is not yet directly identified in laboratory experiments, but observations indicate that it strongly shapes cosmic structure. Ordinary matter falls into the gravitational framework that dark matter helps create. Galaxies then grow within those deeper wells. In this region of the topic, the key question is not simply how far away the web extends. The deeper issue is how the web changes the meaning of motion and return. A traveller moving through a cosmic filament is not moving across still scenery. The galaxies in the filament are carried by cosmic expansion at the same time that they also respond to local gravity. These two effects coexist. On smaller scales, gravity can dominate. In dense regions, galaxies may approach one another, orbit common centers, or merge. On larger scales, expansion separates the great structures from one another. This makes the web a layered environment. Nearby motion may bring objects together, while the wider background gradually pulls distant systems apart. The web therefore contains the first major distinction between a place that remains tied to Earth in the long term and a place that slowly withdraws beyond practical recovery. A dense cluster or filament may seem like a connected province of the cosmos, but only part of that connection is local. The whole pattern is still embedded in expanding space. If a spacecraft could travel outward across millions of light years, its path home would not simply retrace the same geometry. By the time it turned back, the spacing between great structures might be larger. If the outward crossing occurs over truly immense spans, the homeward route could lengthen while the traveller moves along it. This does not mean every remote part of the web is already unreachable in the same way. The cosmic web is uneven. Its crowded nodes contain many galaxies bound together strongly enough that local expansion does not tear them apart. A galaxy cluster is one of these nodes. In a cluster, many galaxies orbit within a shared gravitational domain. Hot gas fills the space between them. Dark matter forms most of the mass. Inside such a system, return from one galaxy to another may still be imaginable in principle, though beyond any human scale of practicality. But between major structures, especially across the deeper voids, the problem changes. A void offers not only distance but also a lack of nearby stepping stones. Matter is sparse, energy sources are rare, and the expansion of space acts over the full breadth of the gulf. The voids are among the calmest and most severe regions in the known universe. They're not empty in an absolute sense. They still contain dark matter, thin gas, and scattered galaxies. yet they are far less populated than the filaments and clusters around them. A journey entering such a region would lose the loose guidance provided by dense cosmic structure. The background sky would still contain galaxies, but the local surroundings would thin into extraordinary emptiness. In practical terms, a void is not only a lack of destinations, it is a lack of assistance. There are fewer gravitational wells to visit, fewer stars to harvest for energy in distant futures, and fewer nearby systems from which a return attempt could be staged. At the scale of the web, gravity and expansion together create a quiet sorting process. Some structures remain bound for ages, others separate ever more strongly. This is especially important under accelerated expansion, as dark energy drives the large-scale growth of space. Distant galaxy groups and clusters become more isolated from one another over cosmic time. The cosmic web seen today is therefore not a permanently available road system. It is more like a structure that slowly tears into separate islands of matter. The web remains visible in the deep sky, but its functional connectivity weakens. In the remote future, an observer inside one gravitationally bound island may no longer see most of the web as it appears now. Many distant galaxies will have faded beyond reach and eventually beyond detectability. For a journey outward, this means that return is threatened long before any traveller reaches the ultimate visible limit of the universe. The danger begins wherever a route crosses from one gravitationally associated region toward another that is only temporarily visible but not durably connected. A destination may be seen, measured, and mapped, yet still lie on the far side of a growing causal separation. The problem is subtle. The sky can present a place clearly while the future forbids exchange with it. Appearance and accessibility begin to diverge. The web also changes how distance itself should be imagined. Between stars in one galaxy, distance can be discussed in relatively stable local terms. Between galaxies in the web, astronomers must distinguish several ways of describing separation. There is the distance when light is emitted, the distance when it is received, and the evolving distance as space expands during the interval. These are not tricks of language. They are essential to the physics. A traveller trying to cross the web would confront the same complexity in a physical form. The target would not merely wait at a fixed mark. It would continue to move with the large-scale flow of expanding space even while responding to local gravity. So this second region refines the first conclusion. The outer horizon shows that some parts of the cosmos are beyond return in principle. The cosmic web shows why that limit is not abrupt at one visible edge. Instead, it is distributed through structure, motion, and time. Filaments gather matter, voids thin it out, clusters bind locally, expansion separates globally. The farther outward the path follows the web, the more the universe behaves not like a static map but like a living geometry in slow motion. In that geometry, a traveller can pass from regions that remain loosely connected to Earth into regions where the bond weakens, stretches, and finally fails. Return is not lost at once. It is eroded by the expanding architecture of the cosmos itself. Within the great web of filaments and voids, the next inward region is the galaxy itself. A galaxy is a vast gravitational system made of stars, gas, dust, dark matter, and the traces of long history written into motion and light. At this scale, the universe no longer appears as a nearly even pattern spread across hundreds of millions of light years. It becomes a collection of separate islands, each with its own internal order. Some are small and faint. Some are giant spirals or swollen elliptical systems containing hundreds of billions of stars. Between them lies intergalactic space, thin and dark. for the question of how far outward one can go before return becomes impossible. Galaxies introduce a more familiar kind of separation. They are distinct homes of matter, but the spaces between them are already so wide that return begins to depend not only on physics in principle, but on time, energy, and irreversible change. A galaxy is not a static lantern hanging in emptiness. It is a moving system shaped by gravity over billions of years. Stars orbit the galactic center, gas drifts, cools, and forms new stars in some regions while dying. Stars enrich the surrounding medium with heavier elements. Small companion galaxies are drawn inward, stretched, and sometimes absorbed. Dark matter surrounds the visible parts in a much larger halo, providing most of the gravitational mass. The visible glow of a galaxy is therefore only part of the structure. The deeper gravitational body extends farther out than the bright disk or central bulge suggests. A traveller leaving one galaxy for another does not merely cross the lit edge of a city-like system. The departure begins within an extended gravitational domain and ends within another. At first sight, a galaxy can seem self-contained enough that travel within it might still preserve the idea of return. After all, stars belong to one common structure and remain bound together over long time. Yet a galaxy is immense beyond ordinary comparison. Even light takes tens of thousands to more than 100,000 years to cross a large spiral galaxy from one side to the other. A journey between stars on opposite sides is therefore not only difficult, it unfolds on timescales that far exceed civilizations as presently known. The issue of never returning starts to acquire a second meaning here. It no longer depends only on the cosmic expansion that separates remote structures. It also arises from the slow but relentless consequences of duration. A traveller may remain inside one galaxy and still pass beyond any realistic path home. Galaxies also move relative to one another. This motion comes partly from local gravitational attraction and partly from the broader expansion of space. In some nearby cases, gravity wins. The Milky Way and Andromeda, for example, move toward one another and are expected to merge in the far future. In other cases, galaxies are carried apart over immense scales. This means that a destination galaxy can belong to one of two broad classes. It can be part of a gravitationally associated region where future contact remains possible in principle, or it can belong to a more distant domain that is slowly withdrawing under expansion. The difference is quiet but decisive. Two galaxies can both be visible in the night sky of a powerful observatory, yet only one may remain within the long-term circle of mutual reach. The intergalactic space between galaxies deepens this problem. Even though it is not completely empty, it is extraordinarily thin. There is diffuse gas, magnetic structure, and occasional high-energy particles. But there is no dense medium through which a traveller can draw easy support. A crossing from one galaxy to another is not like a voyage between islands across an ocean rich with currents, weather, and life. It is a passage through near vacuum lasting so long that the outward and inward legs of the route cannot be treated as equal halves of one simple journey. During the crossing, both galaxies continue to change. Stars are born and die, orbits shift, companion systems merge. The traveller's point of departure and the traveller's hoped for homecoming both move through history. This historical change matters because return is not only about arriving at the same coordinates, it is about re-entering a system that still resembles the one that was left. In a galaxy, the largest structures endure for billions of years, but the details evolve constantly. Star-forming regions disperse, supernovae reshape gas clouds, black holes in galactic centers accrete matter at varying rates. Streams of stars record ancient mergers and continue to spread. A journey lasting millions of years would not come back to the same sky, even if it returned to the same galaxy. The Sun would orbit farther along its path around the Milky Way. Nearby stars would drift into new positions. Constellations would be unrecognizable. The home galaxy would remain, but the living pattern once known would be gone. There is also a practical threshold hidden within the idea of galactic escape. To leave a galaxy, a spacecraft must overcome the gravitational pull of the stars, gas, and especially the dark matter halo. This requires tremendous speed. Even reaching such speed does not guarantee meaningful freedom, because motion must also be directed with precision across immense distances. A slight error sustained over millions of years becomes an enormous miss. Return would require not only another immense change in velocity, but also accurate knowledge of the future motion of the home galaxy and its internal targets. The farther outward the journey extends, the more finely tuned the homeward path must become. For galaxies that are not gravitationally bound to the Milky Way's wider neighborhood, the old cosmological limit returns in a sharper form. Their light may still arrive, their spectra may still be measured, their shapes may still be mapped, yet if they lie far enough away, the expansion of space ensures that a signal or spacecraft departing today could never close the growing gap. The galaxy is then visible but not visitable in any returnable sense. It belongs to the seen universe but not to the shared future of Earth. In this way, galaxies reveal a striking truth. The sky is full of objects that can be known through light while remaining permanently outside any cycle of departure and homecoming. Even among galaxies that remain theoretically accessible in principle, another limit persists. Energy is not a detail that can be postponed. Any return journey across intergalactic distance demands such immense reserves that the difference between possible in physics and possible in reality grows enormous. A civilization might imagine harvesting stellar energy, using long-lived machines, or sending self-sustaining communities rather than crews expecting direct return. But those are changes in the meaning of return itself. The simple human idea of going out and then coming back intact weakens under the scale of galactic distance. The galaxy does not merely enlarge the map, it changes the definition of a completed journey. So this inward step from the cosmic web to the galaxy brings the problem into clearer form. Galaxies are the major islands of the universe, rich in structure, history, and gravity. They are separate enough that the gulf between them becomes its own kind of barrier. Some neighbouring galaxies remain within a shared gravitational future. Many more do not, even within a single galaxy. Distances are so immense that time alone can make return lose its meaning. Between galaxies, expansion, duration, navigation, and energy combine into a harsher conclusion. One may still look outward and see countless stellar cities suspended in darkness. But for many of them, the journey away from Earth would not merely be long. It would pass beyond the point where home could ever be reached again. Inside the wider population of galaxies, the next inward region is the nearby gravitational neighbourhood known as the local group. This is the small family of galaxies that includes the Milky Way, Andromeda, the Triangulum galaxy, and many smaller dwarf galaxies bound to the larger systems. Compared with the immense web beyond, the local group is modest in size, yet it still spans millions of light years, and its members are separated by distances so great that even light moves between them only over spans far longer than recorded human history. Here, for the first time on this outward to inward path, gravity provides a partial resistance to cosmic expansion. The galaxies in this region are not simply drifting apart with the general growth of the universe. They are tied together strongly enough that the family holds its shape against that wider tendency. This makes the local group the first major domain where return remains possible in principle across intergalactic distance, even though it becomes difficult almost beyond measure in practice. The local group is not arranged like a neat cluster with a sharp circular edge. It is a loose association dominated by two large spiral galaxies, the Milky Way and Andromeda, with Triangulum as a smaller but still significant member. Around these larger galaxies orbit many dwarf companions. Some are faint clouds of old stars. Some still contain gas and continue to form new stars. Others appear stretched and disturbed by repeated passages through the gravitational fields of their larger hosts. The region as a whole is shaped by shared gravity rather than by rigid boundaries. A spacecraft moving outward from the Milky Way into the local group would not pass a wall or marked frontier. It would move through an extended space where the Milky Way's influence gradually weakens while the combined pull of the broader group remains. This region matters because it changes the meaning of escape. Beyond the local group, cosmic expansion increasingly determines the long-term relation between large structures. Within the local group, gravity still dominates enough to keep the main members mutually associated. Andromeda is not receding from the Milky Way under expansion in the usual distant galaxy sense. Instead, observations show that it is approaching. Over billions of years, the Milky Way and Andromeda are expected to merge into a larger combined galaxy. This future event confirms that at least some outward journeys beyond one galaxy still occur inside a shared system that remains causally connected. In the most basic physical sense, one has not yet gone so far that return becomes impossible because the destination is being carried away forever. Yet this reassurance is limited. The local group is bound, but it is not small. To cross from the Milky Way toward Andromeda means entering a gulf of dark intergalactic space, still measured in millions of light years. The route lies through a region far thinner than the interior of any galaxy. There are scattered stars outside formal galactic disks, extended halos of gas, streams left by past mergers, and the huge invisible framework of dark matter. But there is no dense road of matter to guide or sustain a traveller. Even within a gravitationally connected family, return becomes fragile because time grows so vast. A journey across the local group would consume such immense duration that the difference between a physical possibility and a meaningful homecoming becomes profound. At this scale, the notion of being unable to return can arise without any absolute cosmic prohibition. The traveller may remain inside a region whose members will stay associated for billions of years, but the time required to move between them may still exceed the lifespan of biological individuals, societies, languages, cultures, and possibly species. Earth itself would continue to orbit the Sun. The Sun would continue its path around the Milky Way. Continents would shift. Climate would change. Human civilization, in its present form, would likely vanish into history long before a traveller reached a neighbouring giant galaxy and attempted the same voyage back. Thus the local group teaches a quiet distinction. Return may remain allowed by gravity and cosmology while becoming lost to time. The dwarf galaxies of the local group sharpen this picture further. These smaller systems, many orbiting the Milky Way or Andromeda, form a nearer outer ring of destinations beyond the main galactic disk. Some are close enough in cosmic terms to have exchanged material and tidal influence with the Milky Way over long history. Their stars often preserve records of ancient formation. Some are rich in dark matter compared with their visible content. To visit such a dwarf galaxy would still mean leaving the principal body of the Milky Way and entering intergalactic space, but not yet crossing the full gulf to Andromeda. Even here, however, the practical challenge is extraordinary. A destination can belong to the same bound group and still be so distant that no ordinary concept of expedition and return survives the crossing. Gravity inside the local group is also not simple. The Milky Way pulls on a departing spacecraft. So do Andromeda, Triangulum, and the diffuse mass of dark matter distributed through the group. This means that motion across the local group is governed by a changing gravitational landscape, not by a single clean escape from one central body into empty freedom. A spacecraft would descend and climb through overlapping wells of gravity. Its trajectory would need to account for the future movement of entire galaxies, not only the present positions seen in the sky. Over long spans, small uncertainties in mass distribution or external disturbance could grow into substantial navigational error. Return would depend on predicting a dynamic system far more intricate than a simple line from one point to another. The local group also marks a rare large-scale refuge from the isolating power of accelerated expansion in the very remote future. While more distant galaxy groups slip away beyond possible contact, the bound members of the local group should remain together and eventually merge into a single larger system. From the standpoint of long-term cosmic fate, this means that some outward journeys within this region stay inside the last great island of matter that Earth's descendants could ever share. This makes the local group an important threshold. Beyond it, many destinations belong to a future permanently detached from the Milky Way. Within it, the family remains one connected realm. But connected does not mean comfortably traversable. It only means that the door is not shut by the expansion of the universe itself. So the main scientific focus of this region settles into view. The local group is the first intergalactic domain where cosmic expansion does not by itself forbid return. Gravity binds the family together strongly enough that its principal members remain part of one common future. Yet the distances inside that family are so immense that return becomes endangered by duration, energy, navigation, and the slow transformation of everything left behind on Earth. One may travel beyond the Milky Way and still remain, in the deepest physical sense, near home. But that nearness exists only on a cosmological map. For any traveller attempting to go outward and later come back, the local group reveals how a journey can remain theoretically reversible, while already passing into a form of separation so extreme that homecoming begins to dissolve long before the laws of physics forbid it. Inside the local group, the next inward region is the outer halo of the Milky Way. This is the vast, faint domain that surrounds the brighter visible parts of the galaxy. It extends far beyond the shining spiral disk and the crowded central bulge. In ordinary images of the Milky Way, the halo is mostly invisible. It does not announce itself with bright lanes of stars or glowing clouds of gas. Instead, it is traced by sparse ancient stars, globular clusters, streams of torn dwarf galaxies, thin hot gas, and above all by a much larger mass of dark matter. It is a region where the galaxy becomes diffuse without truly ending. For the question of how far outward one can go before return becomes impossible. The halo introduces a subtle and important truth. A traveller can remain inside the Milky Way and still move so far from its bright heart that the path home becomes strained by distance, time, and weak but persistent gravity. The halo is not empty space. It contains some of the oldest visible objects in the galaxy. Globular clusters, which are compact spherical groups of ancient stars, orbit in this outer region. Many of them formed early in galactic history, and their stars preserve chemical signs of a time when the universe contained fewer heavy elements. The halo also contains stellar streams, long narrow traces of smaller galaxies and clusters that pass too close to the Milky Way and are slowly pulled apart by tidal forces. A tidal force is the difference in gravity from one part of an object to another. Over time, that difference stretches the object and can tear it into a ribbon of stars. These streams show that the halo is not a still shell. It is a historical record of accumulation, disruption, and slow mixing. The visible halo is only part of the picture. Around it lies the dark matter halo, a much larger and more massive structure inferred from the way stars and gas move. Observations indicate that the Milky Way contains far more mass than can be seen directly. Stars in the outer parts of the galaxy orbit too quickly to be held by visible matter alone. The additional gravity is attributed to dark matter. Its composition remains uncertain, but its effects are clear in galactic dynamics. This means that a spacecraft leaving the bright disk does not quickly enter true freedom. It continues to climb out through an extended gravitational well whose largest part cannot be seen. The halo therefore changes the idea of escape. The edge of visible light is not the edge of the galaxy's hold. For a traveller, the outer halo would feel profoundly different from the star-rich disk. In the disk, stars crowd the sky. Gas clouds, stellar nurseries, and dust lanes create texture and movement. In the halo, the scene thins dramatically. The background remains full of distant stars from the disk and bulge, but the local environment becomes sparse. Nearby stars are rare. Dense clouds of cold gas are uncommon. The galaxy is still present everywhere in a gravitational sense, yet it begins to feel remote in a visual one. This contrast matters because return is shaped not only by physical law, but by the availability of resources and reference points. A sparse region offers fewer places to pause, refuel, navigate by, or harvest energy from over long spans. The hot gas of the halo adds another quiet feature. The Milky Way is thought to be surrounded by diffuse gas heated to very high temperatures. This gas is so thin that it does not resemble an atmosphere in any familiar sense. A spacecraft would not move through it as an aircraft moves through air. Yet over enormous distances, even a very thin medium can matter for the evolution of matter, for the transfer of energy, and for the broader ecology of the galaxy. The halo is therefore not simply a gap between the disk and intergalactic space. It is a transition zone where the galaxy exchanges material with its surroundings, captures smaller systems, and slowly reshapes itself. This outer region also makes clear that return can become difficult long before the galaxy fully lets go. To move deep into the halo requires time, even at speeds far beyond those achieved by present spacecraft. If the journey is slow by galactic standards, then home changes while the traveller remains technically inside the same galaxy. The Sun continues its orbit around the galactic centre. Nearby stars shift their positions. The spiral pattern evolves. The exact route back to Earth becomes a moving target, not because the Milky Way is dispersing, but because every part of it remains in motion. A path outward into the halo is therefore not like walking away from a house that stands still behind the traveller. It is like departing from one moving point inside an immense rotating system. The halo also contains the remains of the Milky Way's past growth. Modern astronomy indicates that large galaxies are built partly by absorbing smaller ones. Dwarf galaxies fall inward, are stretched, and eventually become part of the larger system. Their stars spread into the halo. Their globular clusters join the Milky Way's wider population. This means the halo is a place of incomplete boundaries. Some of its objects are fully settled members of the galaxy. Others are still in the process of being incorporated. For return, this matters because the outer Milky Way is not a neat frontier with a clear gate between inside and outside. It is a broad and changing region where the distinction between galactic and intergalactic begins to blur. A traveller reaching the outer halo has not yet entered the true gulf between galaxies. But one major support has already faded. The dense concentration of stars that defines the disk is far behind. The traveller remains under the galaxy's influence while increasingly distant from the environments where planets, habitats, and abundant starlight are common. This creates a practical threshold. Home is still within the same galactic system, and return remains possible in principle. But the cost of reversing course grows large because the traveller has spent distance and time moving outward without truly leaving the Milky Way. The halo is where one learns that a galaxy is much deeper than its bright appearance suggests. The outer halo is also the region where escape speed becomes especially important. Escape speed is the speed needed to avoid falling back under gravity without further propulsion. Because the Milky Way's dark matter halo contains so much mass, the speed required to leave the galaxy entirely is greater than the bright stars alone would imply. A spacecraft can move far into the halo and still remain gravitationally bound. Unless it reaches sufficient speed, it will not depart forever. This may sound like a reassurance for return, but it is not always so. A bound path can still be long, awkward, and costly to reverse. One may remain tied to the galaxy, and yet drift so far from its inhabited inner regions that a return becomes less a voyage and more a second epic crossing. So this fifth region deepens the argument by showing that the Milky Way does not end where its light fades. The halo extends the galaxy outward into a faint, ancient, and gravitationally powerful domain. It contains old stars, globular clusters, stellar streams, hot gas, and a dominant structure of dark matter. It is quiet, sparse, and immense. A traveller can pass far beyond the familiar disk and still remain inside the galaxy's reach. While already losing the practical ease of homecoming, return has not yet been forbidden by cosmic expansion, and intergalactic darkness has not yet fully begun. But the halo reveals that the road away from Earth becomes severe even before one leaves the home galaxy at all. Inside the halo, the next inward region is the galactic disk of the Milky Way. This is the broad, flattened body of the galaxy where most of its stars, gas, and dust are found. It is the bright band that gives the Milky Way its familiar appearance in dark skies. Spiral arms curve through it. Giant clouds of gas collapse within it and form new stars. Older stars continue their long orbits around the galactic center. Dust absorbs and reddens light, shaping what can and cannot be seen across great distances. In this region, the question of going so far into space that return becomes impossible changes again. The problem no longer depends on the deep separation between galaxies or on the faint outer edge of the Milky Way. It becomes a matter of motion within a crowded, rotating system, where even staying inside one galactic disk can carry a traveller into distances so vast that homecoming begins to fail in human terms. The disk is not a solid sheet. It is a dynamic, layered structure containing stars of many ages, gas in several forms, dust grains, magnetic fields, and the remnants of long stellar history. Some of its stars are young and bright, living short lives before ending in violent death. Others are smaller and dimmer, burning steadily for spans far beyond the current age of civilization. Gas in the disk can be cold and dense enough to form molecular clouds, or warmer and more diffuse between the stars. Dust, though only a small fraction of the total mass, strongly affects vision within the galaxy by blocking starlight and re-emitting energy at longer wavelengths. This makes the disk not only the most populated part of the Milky Way, but also one of the most visually complex. A traveller moving outward through the disk would pass through environments far richer than those of the halo. There are many more nearby stars, many more potential planetary systems, and far more regions where matter is concentrated. Yet this abundance does not make return simple. In one sense, it makes the challenge sharper, because the disk itself is immense. The Sun lies far from the galactic centre, but also far from the outer edge. To travel across the disk means crossing tens of thousands of light years through a medium that is structured, rotating, and never still. Even if a destination remains inside the same galactic plane, the distance is so large that round-trip travel stretches beyond ordinary historical scales. The disk rotates, but not like a rigid wheel. Stars closer to the centre generally complete their orbits more quickly than those farther out. Gas and spiral structure do not all move in exactly the same way. This means the galaxy is in continuous differential motion. Differential motion is motion that changes from place to place within the same system. A traveller leaving the Sun's region and heading to another part of the disk is not moving across fixed scenery. The target system is orbiting the centre at its own rate. The Sun is also moving. The path home must therefore account not only for distance, but for the long-term drift of every major reference point. Return becomes a problem in moving geometry. Spiral arms add another layer. These are not simple fixed lanes of permanent stars. They are better understood as regions where matter becomes more concentrated for long periods, helping to compress gas and encourage star formation. As stars and gas move through the disk, they pass into and out of these denser regions. The arms therefore give the disk its grand visible pattern without acting like solid structures. For the traveller, they offer no stable road. A destination inside a spiral arm may look like a bright marker in a map of the galaxy, but over long spans it remains part of a shifting and evolving pattern. Home, once left behind in the Sun's neighbourhood, continues onward through its own orbit whether the traveller turns back or not. The disk is also the region where ordinary matter becomes plentiful enough that one might imagine building a chain of outward expansion. There are stars, planets, asteroids, comets, and interstellar material in far greater abundance than in the halo. Such abundance may seem to protect the possibility of return because it offers potential sources of shelter, energy, and construction material. In principle, a civilization could spread from star to star through the disk, creating habitats and transport systems over immense spans. Yet such a process would change the meaning of return. A person leaving Earth and later reaching home again after a crossing of large parts of the galactic disk would not simply complete a voyage. The traveller would pass through timescales so long that Earth itself, its biosphere, and the civilization once known would almost certainly have transformed beyond recognition. Return would remain a physical arrival, but lose much of its original human meaning. Radiation and stellar violence within the disk also matter. Supernovae occur here. Massive stars emit powerful winds and intense ultraviolet light. Regions near the galactic centre contain denser stellar populations and more energetic events than the quieter outer areas. Black holes and neutron stars, the collapsed remains of former stars, add to the dynamic character of the disk. A neutron star is the dense core left when a massive star collapses, with matter packed so tightly that a small fragment would weigh enormously. These objects remind the traveller that the disk is not only full of resources, it is also full of hazards distributed unevenly across its breadth. A route through the Milky Way must navigate not a calm star field but a complex living system. The disk further reveals that practical one-way travel begins far earlier than true physical one-way travel. A spacecraft could remain gravitationally bound to the Milky Way and still cross into regions from which a return to Earth would require more time, energy, and coordination than any direct mission could plausibly maintain. The outward and inward journeys would each unfold against the changing motions of stars and clouds. Even if the spacecraft preserved itself perfectly, the origin point would continue to move through the galaxy. Earth would circle the Sun would circle the galactic center, nearby stars would slowly rearrange. The path home would become an exercise in predicting a celestial dance over spans that overwhelm ordinary planning. This disk region also marks the scale at which communication begins to fail, long before physics forbids it. Signals cannot travel faster than light, across large fractions of the Milky Way. Even a simple exchange of messages would require many thousands of years. Advice, warning, coordination, and reunion all slow into almost geological rhythms. A mission outward may still be linked to Earth in principle, but not in any living conversational sense. By the time a reply returns, the world that sent the original message may be gone. Return then becomes severed not by a barrier in space, but by the stretching of time between every act of contact. So the galactic disk presents a rich and solemn middle region in the path inward. It is bright, populated, and full of motion. It contains most of the Milky Way's stars, much of its gas and dust, and the great spiral pattern that defines the galaxy's visible form. Yet it is so large, so dynamic, and so slow on human terms that travelling far across it already approaches a one-way condition. The traveller remains inside the home galaxy, beneath the same broad spiral architecture, but distance, rotation, communication delay, changing hazards, and the long drift of history combine to thin the hope of homecoming. Return has not yet been taken away by the universe. It has begun to be worn away by the sheer scale of the Milky Way itself. Inside the broad disk of the Milky Way, the next inward region is the solar neighbourhood. This is the local volume of interstellar space around the Sun, including the nearest stars, the thin gas between stellar systems, faint dust, magnetic fields, and the moving boundaries of the Sun's own galactic setting. On the scale of the galaxy, this neighbourhood is small. On the scale of travel from Earth, it is already enormous. Here the question of never returning begins to feel more intimate. The traveller is no longer thinking about crossing the whole Milky Way or leaving one galaxy for another. The outward path now runs through the Sun's nearest stellar surroundings, a region close enough to be mapped star by star, yet far enough that return can still fade into impossibility through time, energy, and the slow separation created by motion. The Sun is not fixed in empty space. It travels through the galaxy along with a retinue of planets, smaller bodies, and a large envelope of influence that extends far beyond the visible planets. Around it lie other stars, each with its own motion, history, and likely population of smaller objects. The nearest stars are not arranged in a neat pattern. Some are single stars, some are pairs or larger systems orbiting one another. Some are dim red dwarfs, stars smaller and cooler than the Sun. A red dwarf burns its fuel slowly and can shine for immense spans of time. A few nearby stars are brighter and more massive, but most are modest and faint. Together they create a sparse stellar landscape, not crowded like the imagined skies of fiction, but spread out through distances so large that even the nearest gap is measured in years of travel for light itself. This region matters because it is the first one where interstellar travel becomes concrete rather than abstract. To leave Earth and reach the nearest star is to cross out of the immediate planetary domain and into the local stellar sea. Yet the word sea can mislead. The solar neighbourhood is mostly empty. Between stars lies the interstellar medium, the very thin mixture of gas and dust spread through the galaxy. In the local region, this material is especially diffuse. The Sun appears to lie inside a cavity of low-density hot gas often called the local bubble, likely shaped by ancient supernovae in the broader neighbourhood. Observations indicate that the local interstellar environment has been affected by past stellar explosions. It remains uncertain in detail how all phases of nearby gas are distributed on the smallest scales. For travel, the main point is simpler. The space between nearby stars is not a continuous field of support. It is a vast interval of near vacuum. A voyage through this neighbourhood would therefore spend most of its duration not near stars, but between them. Even the nearest stellar systems are separated from the Sun by distances so large that present-day spacecraft would need many thousands of years to arrive. Faster concepts have been proposed in science and engineering studies, including light sails, fusion ideas, and other advanced propulsion methods, but no mature system yet exists for carrying large crews across interstellar distance and safely bringing them home. This means the solar neighbourhood marks a threshold where return is not denied by the laws of cosmic expansion or galactic structure, but by the severe demands of speed. Without extraordinary velocity, a journey outward quickly becomes longer than the life of the traveller. With extraordinary velocity, new problems arise in energy, shielding, navigation, and braking. Braking is as important as departure. To reach another nearby star is not enough. A spacecraft hoping to return must also slow down at the destination, survive the local environment, depart again, and later slow down once more near the Sun. Every stage costs energy. Every change in speed increases the burden. The outward path from Earth to even a nearby star is therefore not one challenge, but several joined together. A mission that can rush outward without a way to turn around is not a return mission at all. The solar neighbourhood reveals this plainly. At these distances, momentum becomes a trap. The faster the departure, the harder the homecoming. The local stars are also in motion relative to the Sun. Over tens of thousands of years and longer, the pattern of nearby stars changes. Some drift closer, some move farther away. The nearest star today has not always been the nearest in the past, and it will not remain so forever. This matters for return because a destination selected at departure does not remain fixed in a timeless map. The Sun moves through the galaxy. Other stars move as well. Their planetary systems, if present, move with them. A successful round trip through the solar neighbourhood must therefore be aimed not at where things are seen, but at where they will be. Small errors in velocity or direction can become large misses across these distances, and the target itself continues to drift while the spacecraft travels. Communication also begins to fail here in a more personal way. A message to a nearby star takes years to arrive. A reply takes years more. This delay is modest compared with the width of the galaxy, but for human decision-making, it is already profound. Real-time guidance disappears. Rescue becomes unrealistic. Any crew sent outward into the local stellar region would become increasingly independent from Earth, simply because advice cannot arrive in time to matter. Return then depends on systems, planning, and resilience carried from the beginning. The farther outward the craft moves, the less Earth can participate in the voyage except as a fading source of old signals. The local environment adds physical hazards as well. At high speed, even tiny grains of interstellar dust can strike with enormous energy. Thin gas, though sparse, can slowly affect material over long periods. Cosmic rays and other energetic particles pose biological and engineering challenges. Shielding against these threats adds mass, and more mass demands more energy to accelerate and decelerate. The solar neighbourhood therefore behaves like a quiet but unforgiving region. Nothing in it resembles weather, waves, or obvious turbulence, yet its emptiness itself becomes the main hazard. There is little to use, little to hide behind, and little margin for error once a spacecraft has committed itself to the crossing between stars. At the same time, this region remains emotionally and physically close to home by galactic standards. The Sun is still one star among neighbours. Its light would continue to stand out behind the traveller as one familiar point in a sparse local field. The galaxy's wider spiral form would matter less than the simple geometry of nearby stars. This closeness makes the loss of return more striking. One has not yet crossed the Milky Way. One has not yet left the local stellar district. Yet even here, only a few light years from the Sun, the journey away from Earth can already become effectively one way. The cause is not a cosmic wall. It is the combined weight of distance, speed, braking, shielding, moving targets, and delayed communication. So the solar neighbourhood becomes the first truly interstellar threshold in this inward progression. It is a local region of sparse stars, diffuse gas, faint dust, and continuous motion. It contains the nearest destinations beyond the Sun, and therefore the first outward journeys that clearly leave the planetary realm behind. But it also shows how quickly home can become unreachable in practical terms. A nearby star is close only on the scale of the galaxy. For travellers leaving Earth, it is far enough that return already begins to fail unless technology, time, and endurance rise far beyond anything yet achieved. Beyond the nearest stars, but still within the Sun's broader dominion, the next inward region is the Oort cloud. This is the immense distant shell of icy bodies thought to surround the solar system far beyond the known planets and beyond the flattened belt of objects outside Neptune. It is not seen directly as a complete structure. Its existence is inferred mainly from the behaviour of long-period comets, which arrive from great distances and from many directions. Observations indicate that a vast reservoir of icy bodies surrounds the planetary system at extreme range. It remains uncertain in detail how massive it is, how its objects are distributed, and where its outer edge should be drawn. Even with that uncertainty, the Oort cloud marks a profound threshold. It is the outermost region where the Sun still holds countless small bodies in long, weak gravitational attachment. To reach it is to travel so far from Earth that the inner solar system begins to fade into a remote centre rather than a lived environment. The Oort cloud is not like a dense ring or a crowded swarm. It is thought to be extraordinarily sparse. Each icy body may be separated from the next by huge distances. Most are likely small, dark, and difficult to detect unless they are disturbed and begin to fall sunward, where warming turns their ices into gas and dust and makes them visible as comets. A comet is a small icy body that releases gas and dust when heated by the Sun, producing a diffuse envelope and often a tail. In the Oort cloud, however, sunlight is so weak that these bodies remain frozen and inert for immense spans of time. They drift slowly in orbits that can take millions of years to complete. In this region, the solar system no longer feels like a bright family of worlds. It becomes a dim gravitational memory spread through darkness. The Oort cloud matters because it forms a long transition between belonging to the Sun and entering true interstellar space. Its objects remain bound to the Sun, but only weakly. Their orbits can be disturbed by passing stars, the gravitational field of the Milky Way, and possibly the collective effects of the broader galactic environment. A body in the inner planetary system is held tightly by the Sun. A body in the Oort cloud is held gently, almost provisionally. Over the age of the solar system, this cloud is thought to have been built from material scattered outward by the giant planets early in planetary history. Much of that material escapes entirely, some remains in these remote orbits. The result is a distant shell of survivors from the young solar system, lifted so far outward that they now exist in a borderland between home and the galaxy beyond. For a traveller leaving Earth, reaching the Oort cloud would mean a journey vastly beyond the planets, beyond the main belt of icy bodies near Neptune, and beyond the region where sunlight still strongly defines the character of the environment. The sun would remain the central source of gravity, but its light would weaken into an intense star rather than a dominating presence. Solar power, so useful near Earth, would become far less practical. Heat, communication, and navigation would depend more heavily on stored energy, nuclear sources, and inertial precision. Return would begin to change in meaning here because the outward journey would already consume tremendous time even before the traveller left the sun's grasp entirely. A mission reaching deep into the Oort cloud could still be inside the solar system in a gravitational sense, while already far beyond any ordinary possibility of quick homecoming. This region also makes clear that the solar system has no simple final fence. The planetary zone is structured and visible. The Oort cloud is inferred, diffuse, and extended. One may pass outward for a very long time without encountering a sharp moment that clearly says the solar system has ended. Instead, the sun's control weakens gradually. The farther one moves, the more a spacecraft becomes vulnerable to small outside influences accumulated over vast time. A passing star does not need to come very close by everyday standards to alter the orbit of a distant icy body. The tidal pull of the galaxy, weak on inner planets, becomes more relevant for objects so loosely held. In such a region, return is threatened not only by distance but by fragility. The road back is still possible, yet it rests on a weakening bond. The Oort cloud also reveals how slow the outer solar system truly is. Orbits there are not brisk circuits measured in years or decades. They unfold over spans so long that many objects may not return sunward within all of recorded human history. A traveller entering this domain would move through a place where change exists, but mostly on scales too extended for direct experience. This deep slowness affects return in two ways. First, the journey itself would be long unless the spacecraft achieved extraordinary speed. Second, any attempt to use local objects for staging, shelter, or resources would take place in a region with little sunlight, little warmth, and almost no convenient concentration of matter. The Oort cloud belongs to the sun, but it is not generous to travellers. Because the cloud is spherical or at least broadly surrounding rather than confined to one flat plane, it also changes the geometry of departure. The inner planets orbit in nearly the same flattened region. Much of the known architecture of the solar system lies there. The Oort cloud extends outward in many directions. A spacecraft leaving for interstellar space might pass through this cloud almost regardless of which direction it chooses, depending on the exact path and the full structure of the cloud. This makes the cloud less like a road and more like an enormous hinterland. To cross it is not to follow a familiar planetary map, but to move through a remote volume where the sun's influence becomes thin and the galaxy begins to press more noticeably on the shape of orbits. Communication from this distance would also become deeply delayed. Signals travelling at light speed would still take a long time to cross between Earth and a craft in the outer Oort cloud. Real-time control would vanish completely. Even ordinary planning would be burdened by the long wait between message and reply. Earth would remain the origin, but not an active partner in the voyage. Return would depend almost entirely on what the craft carried with it, what it could produce in the dark, and how precisely it could preserve its course over immense spans. A small navigational error made early could grow into a major failure by the time the craft attempted to turn homeward, So the Oort cloud stands as the outermost true frontier of the Sun's loose possession. It is a distant reservoir of icy remnants from the solar system's youth, sparse, dark, and only partly known. It surrounds the planetary realm without announcing itself in bright, visible form. Its objects remain tied to the Sun, but weakly enough that the wider galaxy can disturb them. For the traveller from Earth, this region marks a profound change. One can still say home lies within the same solar system, yet the journey has already entered distances where the Sun's light fades, local support nearly disappears, and return begins to depend on a gravitational connection so stretched that it starts to resemble departure rather than belonging. Inside the distant shell of the Oort cloud, the next inward region is the heliosphere, the great bubble formed by the Sun's outflow of charged particles and magnetic influence. This region is not defined by bright surfaces or rigid walls. It is created by the solar wind, the continuous stream of particles flowing outward from the Sun in all directions. As long as this outflow remains stronger than the pressure of the surrounding interstellar medium, it carves out a cavity in the local galactic environment. That cavity is the heliosphere. Its outer reaches mark a deep threshold in the meaning of home. A traveller crossing beyond it has not yet gone to another star, and has not even fully escaped the Sun's gravity, but has already passed beyond the Sun's protective breath into the wider conditions of interstellar space. The solar wind begins in the hot outer atmosphere of the Sun, where particles gain enough energy to stream outward across the solar system. Near Earth, this flow helps shape space weather, influences planetary magnetospheres, and carries the Sun's magnetic field far beyond the planets. As the wind spreads outward, it thins and slows. It does not continue unchanged forever. Eventually it meets the interstellar medium, the very thin gas, dust, and magnetic field that fill the space between stars. Where the outward pressure of the solar wind can no longer dominate, the heliosphere reaches its outer boundary region. This is not a single clean line. It is a gradual and structured transition in which solar influence weakens and interstellar influence grows. One important feature of this region is the termination shock. A shock is a zone where flow changes rapidly, often slowing and heating. In the outer solar system, the solar wind is thought to slow from faster than local wave speeds to slower flow as it encounters the increasing pressure of the medium beyond. Farther outward lies the helios sheath, a turbulent region of slowed solar wind compressed against the outer boundary. Beyond that is the heliopause, the place where the outward push of the Sun's wind and the inward pressure of the interstellar medium reach a balance. Observations from spacecraft indicate that these regions exist, though their exact shape and variability remain uncertain. The heliosphere is not a perfect sphere. It is shaped by the Sun's motion through local interstellar space, by magnetic effects, and by the changing activity of the Sun itself. This region matters because it separates two kinds of space. Inside the heliosphere, the solar system exists within a volume partly shielded from some of the galactic environment. The Sun's magnetic field and particle flow reduce the intensity of certain incoming cosmic rays. Cosmic rays are high-energy particles moving through space, many of them produced by violent astrophysical processes such as supernova explosions. Outside the heliosphere, that protective screening weakens. A traveller crossing beyond the heliopause would enter a harsher radiation environment shaped more directly by the galaxy beyond the Sun's bubble. Return then acquires a new burden. Home is no longer simply far away. It lies inside a distinct magnetic and particle environment that must be re-entered from outside. The heliosphere also shows that home can be defined by more than gravity. The Sun's gravity extends indefinitely in principle. weakening with distance but never dropping exactly to zero. Yet the heliosphere ends much sooner in a physical and environmental sense. A spacecraft can remain gravitationally bound to the Sun while already travelling outside the Sun's wind bubble. This means the traveller may still belong dynamically to the solar system, while already leaving its most direct physical envelope. The distinction is subtle, but important. Return is not only a question of whether the Sun still pulls the spacecraft inward, it is also a question of whether the traveller remains inside the Sun's protective domain of particles and magnetic influence. The outer heliosphere is also a region of uncertainty and detail. The local interstellar medium around the solar system is not perfectly uniform. Its density, magnetic orientation, and flow relative to the Sun all help shape the heliosphere. The Sun itself changes over time through its activity cycle, affecting the strength of the solar wind. This means the heliosphere breathes to some extent. Its boundaries can move inward or outward. The exact thickness and structure of its outer layers are still studied. Observations indicate that the basic boundary regions are real, and that spacecraft have crossed them. It remains uncertain how the full three-dimensional shape changes over time. For a traveller, this means the crossing out and the crossing back in are not identical events. The boundary is living, not fixed. This region is quiet in appearance but consequential in effect. There are no planets gathered here, no broad belts of ice visible to the eye, and no bright sign saying the Sun's reach is ending. Yet the physics changes, the particle populations change, magnetic conditions change, radiation exposure changes. A spacecraft designed only for the inner or middle solar system would find this environment demanding. Systems built for communication, power, shielding, and long-duration survival would all be tested by the remoteness and by the fading strength of sunlight. Solar energy becomes ever weaker. Communication delays become immense. Earth cannot intervene quickly in any failure. Return, therefore, becomes more dependent on the autonomy of the craft itself. The heliosphere also provides one of the clearest scientific examples of an outward path that feels like departure before gravity fully releases its hold. A spacecraft can cross the heliopause and enter interstellar space in the environmental sense, while still following a trajectory ultimately governed in part by the Sun. The road home then becomes both simpler and harder in imagination. Simpler, because home is still one star system away and the direction remains known. Harder, because the traveller has now entered the medium between stars. However close to the solar system the crossing occurs, the psychological boundary is not the topic here, but the physical one is undeniable. Beyond the heliosphere, Earth lies not merely deeper inside the solar system, but inside a special cavity the Sun creates against the galaxy. The small known spacecraft that have reached this region provide a useful lesson. They move outward steadily, carrying simple instruments, and their communications with Earth already require long delays. They do not turn back. They continue because return would require propulsion they do not possess. Their journeys show that a craft can leave the Sun's wind bubble with relative clarity of direction, yet have no practical means of coming home. This is not because the Sun forbids return. It is because the energy and design needed for a true two-way crossing of such distance are severe. The heliosphere therefore becomes a practical one-way threshold long before it becomes an absolute physical one. So this ninth region draws the solar system inward through a new kind of boundary. The heliosphere is the Sun's vast bubble of charged particles and magnetic influence, formed by the solar wind pressing outward against the local interstellar medium. It includes changing outer layers where the wind slows, compresses, and finally yields. Inside it, the Sun offers a measure of shielding and physical identity beyond simple gravity. Outside it, the traveller enters the galaxy more directly. Return remains possible in principle, but it now requires recrossing not just distance, but a true environmental frontier. The sun still shines behind the traveller, but its breath no longer surrounds the craft. Home has become a place inside a bubble left behind. Inside the heliosphere, but still far beyond the giant planets, the next inward region is the Kuiper Belt. This is the broad outer zone of icy bodies beyond Neptune, extending through a flattened region of the solar system where sunlight is faint. Temperatures are extremely low, and orbital periods grow long, unlike the distant Oort cloud, which is inferred mainly from comet behaviour and is thought to surround the solar system in a vast remote shell. The Kuiper Belt is directly observed. It contains many small icy worlds and dwarf planets, including Pluto and other bodies large enough to hold roughly rounded shapes under their own gravity. This region marks an important return threshold because it is the first clearly populated outer frontier where the solar system still shows an organized planetary structure. Yet Earth is already so far away that travel back becomes ruled by long delay, weak sunlight, and the stubborn mechanics of orbit. The Kuiper Belt is not a solid ring packed with objects close together. It is better understood as a wide and sparse population of icy remnants left from the early formation of the solar system. These bodies are made largely of frozen volatile materials such as water, methane, ammonia, and nitrogen, mixed with rock in varying amounts. A volatile material is one that easily becomes gas when warmed enough. Near Earth, many such substances would not stay frozen for long, but in the Kuiper Belt they can remain solid over immense spans because the sun's warmth is so weak. The objects here preserve something ancient. They are survivors from the era when planets were forming, scattered and sorted by the gravitational action of the giant planets and by the broader evolution of the young solar system. This region has internal order. Many Kuiper Belt objects move in stable orbital relationships with Neptune. Some are trapped in resonance, which means their orbital periods maintain a repeating numerical ratio with Neptune's orbit. Pluto is a well-known example. It orbits the Sun in a path that crosses inside Neptune's distance at some points. Yet the resonance prevents close collision because the timing of the motion remains structured. Other objects occupy more distant, less strongly controlled orbits, while some have been scattered into elongated paths by past gravitational encounters. This means the Kuiper Belt is not merely a storage zone of debris, it is a dynamical landscape shaped by the giant planets, especially Neptune, and by the long memory of planetary migration in the early solar system. For a traveller from Earth, the Kuiper Belt would be the first outer region where distant worlds remain numerous enough to imagine a chain of destinations rather than a single isolated target. There are icy bodies of many sizes, some with moons, some with complex surfaces, and some with signs of past or present internal activity. Pluto, for example, reveals plains of nitrogen ice, mountains of water ice, layered atmosphere, and evidence of an unexpectedly varied history. Other dwarf planets and large Kuiper Belt objects likely hold their own records of freezing, fracture, chemistry, and slow orbital change. Yet this apparent richness does not make the region easy to inhabit or easy to cross. The spacing between bodies is still enormous, and the environment remains one of darkness, cold, and scarcity of immediate energy. Sunlight in the Kuiper Belt is still the same sunlight that falls on Earth, but spreads so thin with distance that its strength becomes small. Solar power is greatly weakened, surfaces remain frigid. Any human-built system operating there for long periods would need to rely heavily on nuclear energy, or some other concentrated internal power source. Heat, which near Earth is often an excess to be managed, becomes a precious resource to be conserved. Machines would have to resist deep cold, brittle materials, and long-term isolation. Communication with Earth would be delayed by hours each way, even at the speed of light. This means that even though the Kuiper Belt belongs clearly to the solar system, it already lies beyond any ordinary notion of direct support from home. Return from the Kuiper Belt is not impossible in the physical sense. Spacecraft can and do move on paths that reach the outer solar system. But return becomes expensive because the outward journey does not simply cover distance in a straight line. It climbs outward through the Sun's gravitational well while also fitting itself to orbital motion. To come back inward requires either giving up energy so that the Sun can pull the craft toward the inner system, or using propulsion and gravity assist with careful timing. Gravity assist is a maneuver in which a spacecraft uses the motion and gravity of a planet to change its own path and speed. In the inner parts of the solar system, such opportunities can sometimes be arranged with useful frequency. In the Kuiper Belt, they become rarer because the spacing of worlds is larger and the useful major planets lie far behind. The region also teaches that a return path can remain open while becoming increasingly impractical. A spacecraft in the Kuiper Belt still orbits the Sun. Earth still circles the same star far inward, but the time required for a round trip grows so large that the mission must become self-sufficient. Systems fail over time, materials fatigue. Tiny navigational errors accumulate. A journey that reaches a distant Kuiper Belt object and then turns for Earth is not only reversing direction, it is enduring a second-long exposure to darkness, cold, radiation, and isolation. The homeward road exists, yet it stretches so far that every weakness in design or planning has years to become decisive. The Kuiper Belt also sits in a region where the solar system begins to look less like a family of dominant planets and more like a wide historical field. The inner planets are compact, bright, and relatively close together. The giant planets are grand and widely spaced, but still commanding presences. In the Kuiper Belt, the architecture spreads out into a broad expanse of smaller icy worlds. This changes how home is perceived. Earth is no longer one planet among several nearby companions. It is a remote inner destination orbiting far inside a system that now seems mostly empty between scattered frozen bodies. Return becomes psychologically irrelevant to the science, but physically the same pattern holds. The farther outward one goes into a sparse region, the fewer nearby opportunities exist to repair, redirect, or gather help. Some Kuiper Belt objects may preserve materials and structures from the solar system's earliest time with unusual clarity, because they have remained cold and relatively undisturbed. Their surfaces can record impacts, volatile transport, seasonal change, and chemical processing by radiation. In this sense, the region is scientifically rich, but scientific value does not erase travel severity. The same cold that preserves ancient matter also resists easy exploration. The same distance that protects these objects from the heat and disturbance of the inner system also places them far beyond quick rescue or routine transport. The Kuiper Belt is therefore an outward frontier where knowledge remains abundant but return grows thin. So this 10th region settles into view as the broad outer plane of the known solar system. The Kuiper Belt is a directly observed population of icy bodies beyond Neptune, sparse but extensive, organized by orbital dynamics and marked by ancient materials. It contains dwarf planets, small frozen worlds, and long records of planetary formation. Yet it is also a realm of weak sunlight, deep cold, large separations, and long delays. A traveller can still point inward and say that Earth remains within the same solar system, but the path back has already become long, energy-heavy, and unforgiving. Return is still allowed. It is simply no longer close to easy. Inside the broad, icy expanse beyond Neptune, the next inward region is the domain of the giant planets. Here the solar system gathers itself into 4 great worlds and their many moons, rings, magnetic fields, and surrounding populations of smaller bodies. Jupiter, Saturn, Uranus, and Neptune do not resemble Earth enlarged. They represent other planetary forms, built mainly from hydrogen, helium, water, ammonia, methane, rock, and ice in different mixtures and under enormous pressure. Their distances from the Sun are still vast, but compared with the Kuiper Belt they define a clearer architecture. This region matters for the question of return because it is the first inward zone where gravity becomes not only an obstacle to leaving Earth behind, but also a powerful tool and danger combined. A traveller entering the realm of the giant planets finds routes that can bend, speed, delay, or trap a mission, sometimes helping the road home and sometimes making it harder to reclaim. Jupiter dominates this region most strongly. It is the largest planet in the solar system, containing more mass than all the other planets together. Its gravity reaches far into surrounding space, shaping asteroid populations, steering comets, and controlling a large family of moons. A spacecraft moving through the outer solar system must treat Jupiter not as a point on a map but as a major landscape of motion. Its gravitational field can be used for a gravity assist, giving a spacecraft extra speed or redirecting its path. Many missions to the outer solar system rely on this method, because carrying all necessary propulsion from launch would be far more difficult. Yet the same power that helps a spacecraft outward can complicate return. A badly chosen path near Jupiter can send a craft too deep into the outer system, into collision danger, or into an orbit that demands large correction later. Jupiter also creates one of the harshest local environments in the solar system. Its magnetic field is immense, and it traps energetic particles that produce intense radiation belts. Radiation here can damage electronics, degrade materials, and threaten any living tissue not heavily shielded. A magnetic field is the region in which magnetic forces act, shaped here by the planet's rapid rotation and internal structure. Near Jupiter, that field interacts with the solar wind and with material from its moon, Io, whose volcanic activity feeds charged particles into the surrounding space. This means that return through the Jovian system is not merely a matter of lining up trajectories. It requires surviving an energetic environment that can punish a spacecraft long before it attempts the inward leg toward Earth. Saturn presents a different version of outer grandeur. Its rings make it visually distinct, but scientifically it too is a giant world with a deep atmosphere, strong gravity, and a complex family of moons. The rings, though broad and bright, are extremely thin compared with their width, and consist mainly of countless particles of ice and rock. Saturn's system contains worlds with thick atmospheres, frozen crusts, possible subsurface oceans, and ancient battered surfaces. For travel, Saturn serves as both destination and crossroads. It lies far enough from Earth that communication delays become long and sunlight is much reduced. Yet it remains near enough that missions can still be conceived without entering the darkest margins of the solar system. Return from Saturn is not denied by distance alone, but the round trip becomes so prolonged that every phase of mission design must be durable over years and often decades. Uranus and Neptune deepen the challenge. They are often called ice giants because heavier volatile substances such as water, ammonia, and methane likely make up more of their internal mass than in Jupiter and Saturn. They are colder, dimmer, and more remote. Their moons and ring systems are less well explored, and their great distance from the Sun gives them a more isolated character. A spacecraft reaching them has already travelled so far that home lies deep in the inner system, small in brightness and slow in communication. Return from such distances requires not only fuel and precise navigation, but also patience on a scale that begins to outgrow human mission culture. Decades may pass between launch and the completion of a major exploration cycle. Any direct homecoming mission for people would multiply the difficulty immensely. The giant planets matter especially because they shape the solar system's transport geometry. Their gravity can fling small bodies inward or outward. In the early solar system, their migrations and interactions likely rearranged vast amounts of material, helping to sculpt the asteroid belt, the Kuiper belt, and perhaps even the distant Oort cloud. Today, for spacecraft, they remain the main engines of trajectory design apart from propulsion itself. This gives them a double role in the story of return. They can open pathways otherwise too expensive in energy, but they can only do so through narrow windows of timing and approach. Miss the right geometry, and the cost rises sharply. Homeward travel from the outer planets is therefore not simply a matter of turning around. It depends on celestial timing, on the relative positions of moving worlds, and on whether a craft has preserved enough flexibility to use them. Their moons add another layer. Some, like Europa and Enceladus, are of great scientific interest because evidence suggests subsurface oceans beneath icy crusts. Others, like Titan, carry thick atmospheres and complex surface chemistry. These worlds might one day tempt ambitious exploration or even long-term robotic outposts. Yet each moon sits inside the gravity well of a giant planet, and often inside a difficult radiation or thermal environment. Reaching such a moon and then returning to Earth is far harder than merely crossing the distance from the Sun to the planet's orbit. It requires descending into and later climbing out of a nested system of gravitational control. A nested system is one in which smaller orbits exist inside larger ones, each adding its own energy costs. The traveller learns here that destination depth matters. One can reach the orbit of Jupiter and still remain far from any easy route back once drawn into the detailed architecture of its moons. This region also clarifies the difference between robotic and human return. Robotic spacecraft can endure long silence, accept narrow margins, and finish a one-way mission with scientific success. Humans require air, water, food, shielding, thermal control, and psychological as well as physical continuity. The giant planet domain stretches these needs almost beyond recognition. Sunlight weakens, rescue is implausible, communication becomes too slow for direct support. Any failure in life support or propulsion would unfold far from immediate help, so even though the giant planets remain well inside the Sun's gravitational realm, they begin to form a practical frontier where return for living crews becomes deeply uncertain. So this 11th region gathers the outer planetary kingdom into one severe landscape. The giant planets are massive worlds with powerful gravity, complex moon systems, magnetic environments, and crucial roles in shaping trajectories across the solar system. They can help a spacecraft outward or inward through carefully timed gravitational encounters, yet they also create hazards of radiation, deep gravity wells, and long isolation. A traveller moving through their realm is still far from the absolute boundaries of the Sun's influence, but already in a place where return depends on precision, endurance, and timing almost as much as on raw distance. Home is still there, circling the same star, but the roads now curve through worlds powerful enough to either guide the traveller back or quietly make the path home much harder to recover. Inside the domain of the giant planets, the next inward region is the asteroid belt. This is the broad zone between Mars and Jupiter, where countless rocky and metallic bodies orbit the Sun. In popular imagination, it is often pictured as a crowded field of tumbling stones packed close together. In reality, it is much more spacious. The objects are numerous, but the distances between them are usually vast. A spacecraft can cross the belt without weaving constantly through visible hazards. Even so, this region is a meaningful threshold in the question of return. It marks the transition between the outer solar system, where long cold journeys dominate, and the inner planetary region, where sunlight grows stronger and travel toward Earth begins to feel more physically attainable. Yet the asteroid belt also shows that coming inward is not simply a matter of being closer. It is a matter of orbital energy, material environment, and the lingering pull of the giant planet that shapes the belt from beyond. The asteroid belt is made of remnants from the early solar system that never combined into a full planet. During the era of planet formation, countless small bodies collided, merged, shattered, and were scattered. In the region between Mars and Jupiter, the strong gravitational influence of Jupiter appears to have prevented material from gathering into a single world. Instead, a broad population of leftovers remains. Some are primitive and carbon-rich, preserving ancient material altered little since the solar system's youth. Some are stony, some are rich in metal, likely fragments of larger bodies that once melted and separated internally before later collisions broke them apart. The belt is therefore not a uniform zone. It is a library of partial histories, each object carrying evidence of heating, impact, chemistry, or survival. This region matters because it offers the first major inward field of solid resources after the outer planets. Water-bearing minerals, metals, silicates, and carbon-rich compounds all exist here in different bodies. To engineers imagining long-term space activity, the belt can seem like a storehouse. Material mined here could in principle support construction, fuel production, shielding, and habitat building. Such possibilities make the asteroid belt look like a hinge between outward exploration and inward return. A traveller coming from the giant planets or beyond might find this the first region where matter is abundant enough to imagine repairing a damaged mission, or building the means to continue home. Yet that promise has limits. Resources in space are not useful merely because they exist. They must be reached, extracted, processed, and moved, and each of those acts demands energy, time, and reliable machinery. The orbital structure of the belt complicates return. Asteroids do not all move together in one tidy path. They occupy a range of distances, inclinations, and orbital eccentricities. Some zones are relatively depleted because Jupiter's repeated gravitational influence destabilizes them. These depleted regions are known as gaps. A gap here is not empty in an absolute sense, but a range of orbits where long-term occupation becomes less common because repeated gravitational nudges drive bodies away. This means the belt is dynamically alive. Its members are not fixed stepping stones waiting in place for travelers. Any mission seeking to use belt objects as part of a return route must match specific moving targets, each on its own solar orbit. The belt also reveals that the path inward is not always easier than the path outward. A spacecraft returning from the outer solar system must reduce its orbital energy relative to the Sun if it is to fall toward Earth's region in a controlled way. This can be done with propulsion, with carefully planned gravity assists, or with long trajectories that trade time for energy. But none of these methods is trivial. Crossing the asteroid belt means entering a zone where many potential destinations exist, yet few offer an effortless line home. In fact, the large number of available bodies can create more choices than certainty. A wrong decision about which orbit to match or when to depart again can add years to the journey. Ceres, the largest body in the belt, shows how rich this region can be. It is classified as a dwarf planet and contains signs of water ice, salts, and a complex geological history. Vesta, another major body, appears to be the surviving fragment of an object large enough to have partially differentiated, meaning it once separated into layers such as crust and deeper interior. These large bodies hint that the belt is not merely rubble. It contains worlds, though small ones, with individual histories and structures. A return mission passing through this region might find them attractive as shelters, way stations, or scientific stations, but they also lie deep inside the sun's gravity compared with the outer planets, which means a craft arriving from far out must still handle the energy of descent and later the precise conditions of continuing inward. Sunlight in the asteroid belt is stronger than in the giant planet region, yet still weaker than near Earth. Solar power becomes more useful again, but not abundant in the way it is closer to the sun. Thermal conditions remain severe. Surfaces can swing between strong heating in sunlight and extreme cold in shadow, especially on small airless bodies that cannot hold heat well. Dust and regolith. The loose fragmented material covering many asteroid surfaces create engineering problems for landing and movement. Regolith can cling, drift when disturbed, and behave unpredictably in weak gravity. These are not barriers to return by themselves, but they show that the belt is not a simple resting place. It is a region where operations remain delicate, even as Earth grows nearer. The asteroid belt is also one of the main source regions for many meteorites and some near-Earth asteroids. Collisions within the belt can send fragments inward, and resonances can gradually shift small bodies onto paths that cross the orbits of the inner planets. This gives the belt a continuing relationship with Earth. Material from it reaches the ground of the home planet over time. In a quiet sense, the return route already exists for rocks. Gravity and orbital dynamics occasionally deliver fragments inward without intention, for spacecraft or travelers. However, controlled return is much harder. Natural inward drift is slow, chaotic, and often destructive. To come home deliberately requires not just being inside the right region, but mastering the mechanics that nature uses blindly. So this 12th region stands as the mineral middle ground of the solar system. The asteroid belt is a wide, dynamic zone of rocky and metallic remnants between Mars and Jupiter, shaped by early planetary history and by the continuing influence of Jupiter's gravity. It contains valuable materials and scientifically rich worlds, and it offers the first strong suggestion that an outward traveller might rebuild or resupply on the way back. Yet it also teaches that proximity alone does not restore simplicity. Orbits remain diverse. Energy must still be managed carefully, and even the abundance of matter does not remove the difficulty of inward passage. Earth is closer now, but return still depends on skill, timing, and endurance rather than on distance alone. Inside the asteroid belt, the next inward region is the inner planetary domain. Here the solar system becomes more compact, brighter, and more intense. Mars, Earth, Venus, and Mercury travel around the Sun in relatively close succession compared with the wide spacing of the giant planets. Sunlight grows much stronger. Orbital periods shorten. Communication delays shrink from hours to minutes. Yet this nearness does not erase difficulty. it only changes its character. In the inner planetary region, return to Earth becomes less a matter of surviving immense emptiness and more a matter of navigating a fast energetic system where timing, heat, and geometry decide whether home can still be reached. The inner planets are rocky worlds, built mainly from metal and silicate rock, rather than from deep envelopes of light gases. Their solid surfaces and relatively compact arrangement give this region an appearance of familiarity when compared with the outer solar system. Mars carries polar ice, dust storms, ancient valleys, and the memory of a wetter past. Earth holds liquid oceans, a dense atmosphere, active geology, and life. Venus is wrapped in a heavy carbon dioxide atmosphere with crushing surface pressure and intense heat. Mercury, nearest the Sun, is airless, heavily cratered, and subject to extreme temperature differences between day and night. These worlds form the most sunlit and energetically active part of the planetary system, and for a traveller coming inward from deep space they seem to offer the first real promise of return. But the promise is narrow. Each orbit is moving quickly, and Earth is not waiting in one fixed place. This is the region where orbital mechanics becomes visibly decisive. Orbital mechanics is the study of how objects move under gravity. In the inner solar system, it governs every possible return. A spacecraft does not simply aim at Earth, as if Earth were a stationary destination in open emptiness. Earth is travelling around the Sun at great speed, and the spacecraft is also moving on its own solar path. To come home, the craft must arrive at the exact place where Earth will be when the two paths meet. Too early, and Earth has not yet arrived. Too late, and it has already passed. The inner solar system therefore does not reward only courage or endurance. It rewards precision in time. Mars is especially important in this region because it is the nearest major outward world that can still be imagined as part of a future human return cycle. It lies beyond Earth's orbit, but not by an extreme margin compared with the giant planets. Even so, travel between Earth and Mars is not always open in a direct and easy way. The planets move at different speeds round the Sun, and the most efficient launch opportunities come in windows separated by long intervals. A spacecraft that misses its proper departure or return window may have to wait many months for the next favourable geometry. This means that even in the inner planetary domain, return can become impossible for long periods, not because Earth is too far away, but because the moving architecture of the solar system temporarily closes the easiest path. Venus creates a different sort of lesson. It lies closer to the Sun than Earth and is often near Earth in cosmic terms. Yet, it is not an easy neighbour. Its dense atmosphere and extreme greenhouse heating make surface operations severe. A greenhouse effect is the warming that happens when an atmosphere traps outgoing heat. On Venus, this effect becomes immense. A mission falling too deep into the Venusian system would face high thermal stress, heavy atmospheric drag, and difficult escape conditions. Nearness to Earth's orbit does not automatically mean nearness to safety. A traveller can be physically closer to Earth than Mars sometimes is, and still be in a far less forgiving environment from which return is harder to arrange. Mercury pushes this truth even further. It lies deepest in the Sun's gravity among the planets. Reaching it from Earth is not easy despite the shorter distance to the Sun, because a spacecraft must shed a great deal of orbital energy to fall inward safely. Coming back out again is equally demanding. This reveals one of the central lessons of the inner planetary region. Distance from Earth is only part of the story. Depth in the Sun's gravitational well matters just as much. To move inward toward the Sun is to gain speed. To return outward toward Earth from a deeper orbit requires energy and careful timing. In that sense, some near places are harder to come back from than some far ones. Sunlight, which was weak and precious in the outer solar system, becomes strong here. This helps power systems and communications, but it also creates thermal problems. Spacecraft must control heat more actively. Surfaces can become dangerously hot, especially closer to the sun. Solar radiation pressure, though gentle, becomes more relevant over long exposures for lightweight structures. The inner region is therefore not simply the comfortable part of the solar system. It is the part where energy is abundant but must be managed carefully. Return becomes easier in some ways because power is more available and Earth is nearer. It becomes harder in others because the sun's influence is stronger, velocities are higher, and mistakes in trajectory can lead quickly to missed opportunities or destructive environments. The inner planets also have atmospheres of very different kinds, and atmospheres complicate return in both helpful and harmful ways. Mars has a thin atmosphere that can assist somewhat with entry, but offers limited braking compared with Earth. Venus has such a dense atmosphere that entry heating and pressure become major hazards. Mercury essentially lacks an atmosphere thick enough to help at all. Earth's atmosphere, by contrast, becomes a useful braking medium for returning spacecraft if the entry is controlled correctly. But that same atmosphere is also a barrier that can destroy a craft if approached too steeply or too fast. Thus, the inner planetary region teaches that Earth is special, not only because it is home, but because its environment offers a narrow combination of gravity, air, and temperature that makes controlled return possible. In this region, communication delays shrink enough that Earth can begin to take part in missions again, though never instantly except in Earth orbit and nearby cislunar space. Signals between Earth and Mars can still take many minutes one way. This means crews and machines beyond Earth still require independence. Even so, compared with the cold silence of the outer solar system, the inner region restores a degree of coordination. Return feels less like an isolated act of endurance and more like a managed meeting between moving worlds. Yet the meeting remains delicate. Earth must be intercepted in time, at the right angle, with the right remaining speed, and with enough system health preserved after the long outward journey. So this 13th region gathers the inner planets into a bright and demanding zone where return begins to look realistic again but never simple. Mars, Earth, Venus, and Mercury move through a compact, fast system governed by strong sunlight and precise orbital geometry. The worlds are closer together than the outer planets, and communication becomes less delayed. Yet the cost of mistakes grows sharper because everything moves quickly, and the sun's pull is stronger. A traveller entering this region is no longer lost in deep darkness, but still must solve the exact problem of how to meet Earth in motion. Home is near now by planetary standards, but return depends on arriving not merely in the inner solar system, but at the right world, at the right time, under the right conditions. Inside the inner planetary region, the next inward domain is Earth's gravitational reach. This is the region where Earth, the Moon, and the motion of nearby spacecraft create a local system within the larger solar system. It includes the space where Earth's gravity becomes the main guide for trajectories aimed at return. Even though the Sun still influences the deeper background of motion, in this region, home is no longer merely a distant planet to be intercepted. It becomes a specific gravitational well to be entered carefully. Return now depends on capture, alignment, and controlled descent through a narrow geometry. A traveller can come very close to Earth and still fail to come home if speed, angle, and timing do not agree. Earth's gravity extends indefinitely in principle, weakening with distance but never falling exactly to zero. Yet in practice there is a broad region around Earth where its pull dominates over that of the Moon for local orbital behavior, and a wider context in which the Sun still matters strongly. This creates a layered environment. A spacecraft approaching from interplanetary space does not simply cross one sharp line and become safe. It enters a changing balance of influences. The Moon circles Earth. Earth circles the Sun. The spacecraft arrives carrying the momentum of its long journey. To convert that arrival into return, the craft must lose enough energy to become bound to Earth rather than merely passing by or being deflected onward into another solar orbit. This is the region where capture becomes central. Capture means that a spacecraft shifts from a path mainly around the Sun to one bound around Earth. That change can happen through propulsion, through atmospheric braking if the craft is close enough and built for it, or through a combination of methods. Without sufficient energy loss, the spacecraft may swing past Earth and continue away. Nearness alone does not guarantee belonging. A return mission therefore depends on a careful reduction of speed relative to Earth, not merely a reduction of distance. This distinction is essential. A craft can reach the neighborhood of Earth while still moving too fast or at the wrong angle to stay. The Moon plays a major role in this region. It is not just a companion world, but a substantial gravitational partner that shapes nearby space. Its orbit creates opportunities and complications. A spacecraft can use lunar gravity to alter its trajectory, reduce fuel demands in some mission designs, or enter pathways that connect different orbital regions around Earth. At the same time, the Moon introduces moving geometry that must be respected. It is not fixed in one place. Its position changes continually, and any useful encounter requires precise timing. The Earth-Moon system is therefore not a simple target but a living gravitational dance, with narrow corridors through which a spacecraft may travel efficiently. Modern orbital studies describe some of these corridors in terms of low-energy transfers and balance points, places where the gravitational pulls of major bodies and the motion of the system create special pathways. A balance point is not a place of perfect rest in everyday terms, but a location in a rotating frame where forces can partly offset one another. These ideas help mission planners design routes that save fuel, especially for robotic missions. Yet such routes often cost more time and demand greater sensitivity to disturbance. For a traveller trying to come home, the existence of elegant pathways does not remove risk. It only changes where the risk lies. Less fuel may be needed, but more patience and precision are often required. Earth orbit itself is not one thing. There are low orbits close to the planet, medium and high orbits farther out, and special paths shaped by the Moon and the rotation of Earth beneath. A spacecraft returning from deep space might aim directly for atmospheric entry, or it might first enter orbit around Earth and descend later. Each choice has consequences. Direct entry reduces the need for prolonged operations near Earth, but demands highly accurate approach conditions. Entering orbit first offers more time to prepare, but requires enough energy and control to perform another major maneuver. In both cases, the problem is no longer how to survive the emptiness between worlds. It is how to transform an incoming cosmic path into a stable local one. This region also reveals how narrow the margin of successful return can be. If the approach is too shallow, a spacecraft entering the atmosphere may skip back out, failing to descend properly. If it is too steep, heating and deceleration can become destructive. If the craft aims for orbit but burns at the wrong time or with the wrong strength, it may remain on an unsafe path, re-enter too soon, or drift away again. Earth's gravitational reach therefore does not behave like a wide welcoming harbour. It behaves more like a precisely shaped inlet that must be entered under controlled conditions. The closer the traveller comes, the less forgiving simple mistakes can become. Communication delays are much shorter here than in the wider solar system, but they do not disappear entirely for all operations. More importantly, the speed of events increases. During approach to Earth, crucial changes in trajectory and heating can happen quickly. Decisions made minutes too late may no longer matter. This means that even near home, autonomy and pre-planned accuracy remain vital. Earth can once again guide, observe, and communicate much more effectively than it could during interplanetary travel. Yet the final approach still depends heavily on what the spacecraft already knows how to do. The region around Earth is also crowded in a modern technological sense. Artificial satellites, orbital debris, stations, and communication systems now occupy parts of near-Earth space. This is a recent layer added to the ancient gravitational structure. It does not dominate the physics of return from deep space, but it does add practical complexity. A craft entering Earth's vicinity must fit into a domain that is no longer purely natural. Paths may need to be coordinated. Approaches may be constrained. Home is not only a planet now, it is also an active orbital environment shaped by human presence. Most importantly, Earth's gravitational reach makes plain that return is a matter of controlled surrender. The spacecraft must give up speed, give up freedom of path, and accept the exact conditions imposed by the Earth-Moon system. Farther out in the solar system, a craft can survive while remaining loosely tied to the Sun. Near Earth, survival depends on becoming tightly coordinated with one particular world. The traveller is no longer simply moving inward. The traveller is being drawn into a local structure that demands accuracy at every step. Home is close enough to see in detail, yet still not secured until the craft is truly captured and guided toward descent. So this 14th region narrows the problem of return to the immediate gravitational environment of Earth and the Moon. Here distance has largely been overcome, but geometry becomes supreme. The spacecraft must transition from solar travel to Earth-bound motion, navigating the pull of Earth, the moving presence of the Moon, and the exact conditions required for capture or controlled entry. A mission may come all the way back from the outer reaches of space and still fail in this final local region if momentum, timing, and alignment do not match. Home is no longer far away, it is very near, yet it remains a destination that must still be won. Inside Earth's gravitational reach, the final inward region is the threshold of low orbit, atmospheric entry, descent, and landing. At this smallest scale in the outward to inward journey, the question of never returning is no longer about galaxies, interstellar darkness, or the cold margins of the solar system. It becomes a question of controlled survival. The traveller has come back through all the larger regions of space and now faces the most delicate transition of all. Earth is directly below, its air, oceans, land, weather, and gravity are close. Yet the final act of return is not guaranteed by nearness. It depends on passing from the vacuum of space into the dense atmosphere of a living planet without burning, skipping away, breaking apart, or missing the intended place of arrival. Low orbit is the last stable region before this transition. A spacecraft here circles Earth quickly, still in free fall, balanced between forward motion and the pull of gravity. It has not yet landed. It has only postponed landing by moving sideways fast enough that the ground curves away beneath it. This is an important idea because it shows that being close to Earth is still not the same as being home. A spacecraft in low orbit may be only a few hundred kilometers above the surface, yet it remains fully dependent on machines, stored resources, and careful control. Air cannot be breathed outside the craft. Temperature must still be managed. Radiation is reduced compared with deep space, but not absent. Return is near, but still unfinished. To descend from orbit or from a direct return path, a spacecraft must lose speed in a controlled way. This can be done by firing engines, by using the atmosphere itself as a braking medium, or by combining the two. The atmosphere becomes the final great tool of return. Unlike airless worlds, Earth offers a thick layer of gas that can absorb enormous amounts of kinetic energy. Kinetic energy is the energy of motion. A spacecraft arriving from orbit or from beyond Earth carries tremendous kinetic energy simply because it is moving so fast. That energy cannot vanish. It must be transferred, mostly into heat in the surrounding air and on the heat shield of the craft. The final approach home is therefore an act of turning motion into heat and then surviving the process. Atmospheric entry is severe because air grows denser rapidly as altitude decreases. At the highest edge of the atmosphere, the gas is still extremely thin. Deeper down, it thickens enough to compress violently in front of a fast-moving spacecraft. This compression heats the air to extraordinary temperatures. The heat shield protects the craft by absorbing, reflecting, or carrying away this heat. In some designs, material slowly chars and erodes, taking heat with it as it peels away. In others, insulating materials help keep the inner structure cooler. The principle is simple even if the engineering is not. Return to Earth depends on allowing the atmosphere to slow the craft while preventing that same atmosphere from destroying it. The angle of entry is one of the smallest and most decisive details in all of spaceflight. If the spacecraft enters too steeply, deceleration and heating can become extreme. The structure may fail, the forces on the crew, if any are aboard, may rise beyond safe limits. If the entry is too shallow, the craft may fail to descend deeply enough and can skip back upward, returning to space on a long unwanted path. This narrow acceptable range is one reason the final threshold is so delicate. After crossing the solar system or even returning from the moon, the mission can still be lost in the last minutes because Earth's atmosphere is both a shield and a blade. It protects by braking, but only if the approach is exact enough. Descent continues after peak heating. Speed falls. Plasma around the craft, created by superheated ionized gas, may briefly interfere with communication. The spacecraft passes from the fiercest part of entry into denser air, where parachutes, lifting surfaces, or powered descent may take over depending on the vehicle design. A plasma is a gas so energized that electrons separate from atoms, changing how the gas behaves. During this phase, the craft is no longer a deep space traveler in the old sense. It becomes an object inside weather, wind, pressure, and gravity as lived on a planet. Small atmospheric variations can matter. Winds can shift the landing point. Cloud, dust, sea state, or terrain can shape the final outcome. Home is now a physical environment with texture and motion. Landing is the last reduction of freedom. On water, the craft must survive impact, float, and await recovery if it is designed that way. On land, it must manage vertical speed, stability, and surface conditions. Some vehicles descend under parachutes. Some use wings to glide. Some rely on engines to soften the final contact. Each method solves the same fundamental problem. The craft must pass from orbital or interplanetary speed to zero relative motion, with the ground without exposing its occupants or systems to fatal forces. All the great distance of space is compressed here into a short sequence of exact actions. There is no room left for broad adjustment. The spacecraft either lands within tolerance or it does not. This final threshold also shows why return is more than arrival. A traveller may reach Earth orbit sick, exhausted, damaged, low on power, or carrying systems degraded by months or years in space. The atmosphere may be the planned braking system, but it can also magnify any weakness left unresolved. Guidance errors matter more, structural damage matters more, thermal protection flaws matter more. Re-entry is not the place where a mission recovers from neglect. It is the place where every earlier choice reveals its quality. The long road home remains present in the last minutes, because the condition of the returning craft is the sum of the whole outward and inward journey. Earth's surface itself completes the meaning of return. Oceans, air pressure, gravity suitable for long-term life, and access to food, water, and shelter make Earth not merely a landing site, but the only currently known world that naturally restores human bodies and ecosystems at full scale. A spacecraft can return to orbit, but home in the fullest sense requires re-entry into this biosphere. The biosphere is the global region of life, including land, water, and air shaped by living organisms. This is the innermost region of the whole script, not because it is the smallest in distance alone, but because it is the deepest in consequence. Every larger region outward can be crossed only temporarily. Earth alone is the place where the traveller stops needing a machine between body and world. So the final answer settles here in the smallest and most exact region. One can go astonishingly far into space and still, in principle, come back if energy, time, and physics allow it. But at the innermost threshold, return is decided by the narrow art of atmospheric entry and landing. Distance has already been conquered. The last danger is control. Earth waits below not as an abstract point in space, but as a real planet with air dense enough to save or destroy, gravity strong enough to capture or crush, and a surface that must be met gently after a journey of enormous speed. The farthest outward limits begin with cosmic expansion. The final inward limit ends with fire, air, and the thin margin of a safe descent. The journey inward now comes to rest in the simplest fact of all. Space can be crossed in thought from the visible edge of the universe to the upper air above Earth, and at every scale the meaning of return changes. In the outermost cosmos, return fails because expansion and the finite age of the universe divide reality into regions that can no longer share a future. In the realm of galaxies, return begins to fade under distance and time, even where gravity still binds local structures together. Inside the Milky Way, the same fading continues through the halo, the disk, and the sparse neighbourhood of the Sun. In the outer solar system, home remains part of the same star system. Yet sunlight weakens, travel time lengthens, and the path back grows more demanding with every orbit crossed, closer to Earth. The challenge narrows from vastness to precision, until the whole question of homecoming depends on one controlled passage through air. What appears at first to be a single line between departure and return is instead a layered set of thresholds. Some are absolute, some are practical, some are measured not only in distance but in energy, radiation, communication delay, orbital timing, and the slow transformation of everything left behind. A traveller may remain physically able to return while already losing the world that once gave return its meaning. In that way, space is not only a map of far places, it is also a measure of how fragile home becomes when stretched across time. Earth remains unusual in every inward layer. It is not simply the point of origin, it is the one known world where gravity, atmosphere, temperature, chemistry, and life meet in a form that allows effortless belonging. Every outward step makes that balance seem narrower and rarer. Every inward step restores it piece by piece, until the final descent ends the long dependence on machines and sealed walls. The farthest one can go before never returning depends on which kind of return is meant. Physics sets one limit, human life sets another, time sets another still.